Today we're going to be learning about vertex form. So the first thing we're going to do is looking at two sets of equations and seeing what we notice and what we wonder. So looking at these two sets, okay, here's set number one with f of x, g of x, and h of x, and set number two with p of x, q of x, and r of x. And what do you notice? What do you wonder? Well, I notice in both of these that each set has three equations. All of the equations in each set are in function notation. We have one that's in standard form for each set, one that's in factored form for each set, and then one that's in some other sort of form that we're not exactly sure what that is yet. What do we wonder? Why are they grouped this way? Is there a special name for this last form? Okay, the first ones were standard, the next ones were factored. So is there some sort of name for those last ones? Are they all the same? Meaning, is all of this group equivalent and all of this group equivalent? So those are things that we notice and wonder about those equations. All right, so we have our two different sets of equations that we saw, and the expressions that define the output are equivalent. So these three are equivalent and these three are equivalent, okay? So the expression that defines h here is written in what we call vertex form. We can show that it's equivalent to the expression defining f by expanding the expression. If we have the quantity x plus 2 squared minus 4, that x plus 2 squared means we write it twice, we multiply it, we distribute to get this, and then when we combine like terms, we end up with x squared plus 4x. So this was vertex form, this is standard form, they're equivalent. So number one says to show that the expressions defining r and p are equivalent, okay? So we're going to start with r. So that's -1 times the quantity x minus 3 squared plus 4. So that means that we need to take that x minus 3 and it gets written twice. So let's keep our -1 outside. When we distribute this, x times x is x squared. X times -3 is -3x. -3 times x is -3x, and -3 times -3 is a positive 9. And then we still have, our parenthesis there, and then we still have plus 4. So the next step is to distribute that negative through. So that's going to change the sign of all of these. Now we could also have combined like terms here if we wanted before that, but that's okay. So we have -x squared plus 6x minus 5, which is what p of x equaled up here. So we just showed that those two things are equivalent to each other. Okay. Number 2 says here are the graphs representing the quadratic functions. Why do you think expressions such as those defining h and r are said to be written in vertex form? So up top, they told us that h was x plus 2 squared minus 4, and they told us that r was -1 times the quantity x minus 3 squared plus 4. So why do you think those are written in vertex form? Well, if we're looking at the vertex of this, the vertex here has the coordinates -2, -4. So we kind of see there's a positive 2 there, but that -4 stays the same. Let's see what happens over here. So our vertex for this one is the point 3, +4. So the 3 is the opposite there, and then the 4 stayed the same. So is that consistent here? Here, the x coordinate of our vertex is the opposite, the y coordinate stays the same. The x coordinate of our vertex goes the opposite, the y coordinate stays the same. Okay, so we have those things that are happening. So let's investigate a little bit more here. Okay, so it tells us to play around with parameters. So we're going to use graphing technology. We're going to graph y equals x squared and then add different numbers to x before it is squared. Okay, so we're going to observe how the graph changes. So if we're looking at this here, I went ahead and graphed y equals x squared, and then I added 4 before I squared it, and I subtracted 3 before I squared it. So let's see what those look like. So here, when we added 4 before we squared it, that moved it over to the left. Okay, it actually moved it left. And when we subtracted this 3, that's the green graph over here, it actually moved it right 3 spaces. So adding a number to x, let me move this out of the way here, moves the graph left. And subtracting a number from x moves the graph right. Okay? And that's going to happen no matter what numbers you come up with. So the next thing it asks us to do is to graph the y equals the quantity x minus 1 squared, then experiment with each of the following changes to the function and see how they affect the graph and the vertex. So we're going to look at y equals x, the quantity x minus 1 squared. So remember, what's that going to do to the graph if it's a minus 1? It's going to actually move it right 1. So there is our function where we have graphed y equals the quantity x minus 1 squared, and it did move the vertex 1 space to the right. So now let's see what happens if we add a constant term to the quantity x minus 1. So if we add 5 to it, or we subtract 9 to it, so what happened there? When we added the 5, it moved it up 5 spaces. When we subtracted the 9, if we get rid of this for a second, it did move it down 9 spaces there. Did it do anything to the x-coordinate of the vertex? Nope, not at all. So let's rank those things. All right, so adding a constant moves the vertex up. Subtracting a constant moves the vertex down. And we're also going to say the x-coordinate of the vertex is not changed. So we still had -1 as the vertex of all of those. Okay, let's see what our next piece says. It asks us to multiply the x minus 1 squared by different coefficients. Okay, so if we keep our y equals x squared, but we're going to multiply it by a few different coefficients and see what happens. So if I can get my stuff happening over here. All right, so we still have our original graph, the y equals the quantity x minus 1 squared. So that's there. It's moved it right 1 space. Let's see what happens when we multiply it by 3, by -2, or by 1/2. So what happens when you multiply by those different coefficients? So we notice that all of them have the same vertex, so it doesn't change the vertex, but it does change whether the graph is wider or narrower, and it changes if it opens up or down. What made the orange one face down? Yeah, that negative there. In relationship to the original, the purple is the skinniest, and then the orange is the next skinniest. The widest of them would be the red, the y equals 1/2 times the quantity x minus 1 squared. Okay, so let's see. Multiplying the squared term does not change the vertex. Makes the graph skinnier or wider, or you could say more narrow, okay? And it could also makes the graph flip if multiplying by a negative. So a lot of those same changes that happened before also happen in this situation, okay? So then let's see when we put all of this stuff together, what happens. So we're gonna fill out this table. And it says, without graphing, we want to predict the coordinates of the vertex of the graphs of these quadratic functions and predict whether the graph opens up or down. Okay, so we're going to ignore this last, so I'm going to cover that up for right now. So just looking at these, we should be able to determine if they face up or down, okay, by looking at the leading coefficient here. Okay, so which of these are going to open up and which of them are going to open down? So here, this is positive, so it's going to open up. Positive out front, so that's up. This is a negative out front. Remember, multiplying by the negative is going to make it flip down. Here, it's positive, so up. 1/2 is positive, doesn't matter, there's a fraction that's going up, and then the negative here means that it's going to flip down. Okay, so then the vertex, remember the number inside the parentheses with x is going to move it the opposite of what you think for the x coordinate, and the number added or subtracted outside is going to give us the y coordinate exactly as it is. So that means that we're going to take that positive 10 and make it negative 10. Since there's nothing being added there, we have 0. For the next one, we have a negative 4 as the inside piece here. It means we're going to change it to a positive 4, and the 8 is on the outside. That's going to be the exact same vertex for the third one down here. The only difference is that this one's going to face up and this one's going to face down. They're the exact same thing otherwise. Here for this next one, we have nothing added or subtracted with the x, so that means our x coordinate is 0, and then the negative 7 stays as our y coordinate. Here, we will take that positive 3 and make it a negative 3. Negative 5 on the outside stays the same. And then the 100 inside changes to negative 100, and the positive 50 on the outside stays the same. Okay. So now it says use graphing technology to check your answers. Okay, so we know that those are true. Then we're going to complete the last row of the table. So if we have y equals a times the quantity x plus m squared plus n, that means that the x coordinate is going to be whatever's in here and the opposite of it, and the y coordinate is going to be just that n. In terms of which way it opens, this is going to depend. So it depends on a. Whatever this a value is, it's going to tell us if it faces up or down. Okay? Last thing to look at says, are you ready for more? What is the vertex of the graph? So this is our vertex here. We have to be careful to look at what they're counting by. So on the x-axis, they're counting by 1s, and on the y-axis, they're counting by 2s. That means our vertex is going to be the point 3, negative 4. Now, we're going to write an equation for that. So we need y equals x minus 3, since that was a positive 3 squared, and then the minus 4 stays the same. However, we do notice that this value of 0, 14 is, this point is there. So if I plug in 0 for this, 0 minus 3 is negative 3. Negative 3 squared is 9. 9 minus 4 is not 14. So let's see what happens if we put a 2 in front of this. So 0 minus 3 is negative 3. Negative 3 squared is 9. 9 times 2 is 18, and 18 minus 4 is 14. So that's it. So this is the big piece right here. If the number is being inside, then you need to switch it to be the opposite for the x coordinate, and the number added or subtracted on is going to be the y coordinate of your vertex. And that's it.